in the time it takes you to just to blink, right? The memory inside your computer just executed over 200 million independent data transfers.
Oh, at least. It's moving incredibly fast.
Right. And if even a single one of those microscopic electrical pulses is off by a fraction of a nanosecond, or, I mean, if a stray cosmic ray just randomly flips a single bit, your entire system crashes.
Yeah, totally blue screens.
So, welcome to today's custom deep dive, where we are investigating the absolute microscopic chaos that makes instant computing possible. We are talking about your system memory, specifically random access memory, or RAM.
Which really is the invisible battleground of your computer. I mean, you probably already know RAM is your system's active workspace. We don't need to rehash the basic difference between memory and a storage drive today.
No, we're going way past that.
Exactly. But what most people don't realize is just how violently fast and complex that workspace has to be to, keep a modern processor fed with data.
And to guide us through this, we are pulling directly from a really highly technical set of sources. We're looking at Professor Messer's CompTIA plus certification training notes.
Specifically, the 220-1201 material.
Right, the ones covering memory technologies. Because this is the material designed to teach actual IT professionals how hardware functions in the real world.
Not just the theory, but the underlying math and the actual physical limitations of the silicon.
Yeah, which is the perfect lens for this deep dive.
Right.
I mean, we aren't looking at consumer marketing fluff today. We're going straight to the architectural level of memory modules.
Right. We're going to look at the math behind how memory catches and corrects its own errors at the speed of light.
Which is mind-blowing.
It really is. And we'll look at the physical engineering constraints that dictate how you should actually configure your own systems at home.
Okay, let's unpack this. Let's start right at the physical connection, because before we talk about how fast it is, we have to establish what it actually is.
Right, the physical shape of the workspace.
Yeah, so I usually picture RAM like the top of a physical desk. It's where you actively work, where you spread your papers out, and the hard drive is like the filing cabinet in the corner where you put things away for long-term storage.
That's a classic analogy, and it's perfect. The CPU literally cannot touch your data unless it's pulled out of the filing cabinet and placed onto that desk first.
So physically, we know RAM isn't just a bunch of loose chips scattered across the motherboard. It's this highly engineered module. And the industry term is a DIMM, right? D-I-M-M.
Yes, DIMM, which stands for Dual Inline Memory Module.
Dual inline. What does the dual part actually signify there?
So it refers to the electrical contacts. If you take a DIMM, that rectangular printed circuit board, and you look at the bottom edge, you will see a row of golden pins.
The little gold teeth.
Exactly. Now turn it over, and there is another completely separate row on the back.
No.
So dual inline means those two sides are completely independent electrical pathways. When you snap that module into your motherboard, it establishes a data width of 64 bits.
64 bits. Okay. So every single time the system talks to that DIMM, it is communicating in wide 64-bit chunks of data.
Every single time.
I picture it almost like the short-term working memory of the human brain during a high-stakes math test.
Oh, I like that.
Like you need to hold multiple complex numbers in your head simultaneously to solve the equation. So the wider that 64-bit communication channel is, the more complex numbers your computer's brain can basically juggle at the exact same moment.
That is an excellent way to visualize it. And that 64-bit chunk is a critical piece of math we will come back to in a minute when we look at how memory speed is calculated.
Right. But physically, that standard DIMM is what you find in a large desktop PC.
Yeah, they're fairly long.
But for laptops and ultra-thin mobile devices, obviously, engineers had to severely compress that workspace. So they created the SO-DIMM, or Small Outline Dual Inline Memory Module,
Right, small outline version.
which is exactly half the physical length of a regular desktop DIMM. And instead of standing vertically, it usually presses down horizontally against the motherboard to save space.
Exactly, to keep the laptop thin.
But wait, I have to push back on this design a little bit. If this SO-DIMM is inherently half the physical size, aren't we sacrificing half of our laptop's performance just to keep the device thin?
It definitely seems like you should lose something, but you don't. The underlying technology is actually identical.
Really? Even at half the size?
Yes. A 16-gigabyte SO-DIMM holds the exact same amount of data and pushes the same 64-bit data width as a massive desktop DIMM.
How do they manage that?
Well, engineers achieve it mostly through much higher density memory chips. But more interestingly, they manipulate something called memory ranks.
Memory ranks. Okay, that term didn't show up for me until we really dug into the IT certification notes. What exactly is a rank?
So a rank is a specific set of memory chips on the module that the system accesses simultaneously to create that full 64-bit block of data we just talked about.
Okay.
Some memory modules are single rank. That means all the chips needed for that 64-bit block are basically accessed at once. But some modules are dual rank. They effectively have two completely separate 64-bit sets of chips crammed onto the exact same physical stick.
Oh, wow. So it's almost like a double-sided menu at a restaurant.
Yeah, that's a good way to put it.
You can only read one side of the menu at a time. That's the single 64-bit block. But you have twice as many options available right there in your hands without having to ask the waiter for a completely different menu.
Precisely. The processor can only pull data from one rank at any given millisecond. But having dual rank memory allows the memory controller to queue up commands on the second rank while the first rank is still busy transferring its data.
So it just seamlessly bounces between them.
Exactly. It physically compresses more usable, highly efficient memory into the exact same footprint, which is how a tiny SODIMM can perform on par with a giant desktop module.
That perfectly bridges the gap between the physical layout and the actual movement of data. Because just knowing the shape of the module doesn't really explain the chaos of how fast the information is moving.
No, not at all.
So how does the processor orchestrate these massive 64-bit chunks of data without everything just violently colliding?
Well, it requires absolute precision,
Right.
which is why modern RAM is synchronous. The full acronym is SDRAM, Synchronous Dynamic Random Access Memory.
Synchronous, meaning it syncs to something.
Right. The motherboard has a system clock. It's literally a quartz crystal that pulses at a very specific electrical frequency.
Okay.
Every component in the system, the CPU and the memory included, uses this common clock to keep track of their operations.
So it's like a metronome for a massive orchestra.
Yes. Perfect analogy.
You have all these different components playing at blinding speeds, but because they can all hear the exact same tick-tock, tick-tock of the motherboard's clock, they stay perfectly aligned.
Yes. And in the earliest iterations of synchronous memory, transfers happened at a single data rate.
Meaning one transfer per tick.
Exactly. On every tick of the metronome, the memory would transfer one 64-bit block of data. Tick, transfer, tack, transfer.
But processors got way faster, and I'm guessing a single data rate just wasn't enough to feed them anymore.
No, they were starving for data. And what's fascinating here is how engineers bypassed this physical limitation.
Because you can't just turn up the metronome infinitely, right?
Exactly. Instead of just violently turning up the speed of the clock, which generates massive amounts of heat and electrical instability, they introduced DDR, double data rate.
Ah, DDR. You see that acronym everywhere.
Right. They engineered the memory to transfer data on the leading edge of the clock signal, so the tick going up, and the trailing edge, the talk coming down.
Wait, so the musicians essentially learned how to play a note when the metronome swings to the left and play another completely different note when it swings back to the right.
Yes, exactly. You double the amount of information moving in the exact same span of time.
Wow.
You extract maximum efficiency from the exact same clock speed. And this brilliant move led to the generational march we see today. DDR3, DDR4, and now DDR5.
And each iteration just refines that double data rate architecture.
Right, usually lowering the voltage required and massively increasing those transfer speeds.
But, those generational improvements introduce a super confusing reality when you are actually looking at IT specifications or just shopping for parts.
Oh, the naming conventions.
Yeah.
It's a nightmare.
Professor Messer's notes highlight two totally different naming conventions for the exact same physical stick of memory.
Yep.
Like you'll see a module labeled as DDR4 3200, but right next to it on the box, it's also called PC4 25600. Why on earth do we need two different numbers that sound absolutely nothing alike?
This is a classic point of confusion that IT professionals literally have to memorize and master. It all comes down to what specific speed you are measuring.
Okay, wait on me.
The first number, DDR4 3200, tells you the mega transfers per second. That module is executing 3,200 million transfers every single second.
Which sounds incredibly fast.
It is.
So where does the 25,600 come from? Do they just make it up?
No, it comes from calculating the total bandwidth. Remember earlier when we established that a standard DIMM operates with a 64-bit data width?
Right. The dual inline contacts push chunks of 64 bits.
Well, 64 bits is exactly 8 bytes of data.
Because there's 8 bits in a byte.
Right. Exactly. So if you take those 3,200 million transfers and multiply them by 8 bytes per transfer...
You get 25,000.
Yes.
Yeah.
25,600 megabytes per second. That is your total peak throughput.
Oh, wow.
So PC4 25600 is simply the total bandwidth,
Hmm.
whereas DDR4 3200 is just the raw transfer rate. It's literally two mathematical ways of describing the exact same physical capability.
Just multiply the transfers by 8. That is such a crucial piece of math to understand when evaluating system specs. You're not buying two different things.
Exactly.
But is the transfer rate the only metric of speed that matters? Because
Yes.
I feel like I've seen memory with massive transfer speeds that still somehow benchmarks slower than an older module.
Ah, you're touching on the CAS latency, or column adjust strobe latency.
Latency, the waiting game.
Right. Throughput is how much data you can move all at once. Latency is how long the processor actually has to wait for the memory to respond to a request in the first place.
So how does that work physically?
Memory chips are organized internally almost like a massive spreadsheet, a huge grid of rows and columns. When the CPU asks for data, it has to specify the exact row and column to find it.
And CAS latency is the actual delay in retrieving it from that specific cell.
Exactly.
Yeah.
CAS latency, which is often listed as CL16 or CL36 on the module, is the number of clock cycles it takes for the memory to locate the data in that column and actually make it available on the output pins.
Oh, I see. So you can have a blistering fast throughput of 25,600 megabytes per second, but if the CS latency is incredibly high.
The processor still spends wasted clock cycles just waiting for the transfer to even begin.
So throughput is the width of the pipe, but latency is how fast the valve actually opens.
Precisely. And this incredible speed, moving billions of bytes while managing these microscopic latencies, it brings us to a terrifying vulnerability.
The bit flips.
Yes, the bit flips.
This part of the notes was wild to me.
When you are moving that much electrical voltage across a physical motherboard, interference is just inevitable. Heat, power fluctuations, or, and this sounds like science fiction, literally cosmic rays from space penetrating the atmosphere.
Wait, actual cosmic rays?
Yes, they can strike a memory chip and cause a single bit of data to flip from a 1 to a 0.
That is insane. Like, if a bit flips in the short-term memory of my laptop while I'm editing a photo, I don't know, maybe a single pixel turns the wrong shade of blue for a fraction of a second.
Right, you'd never notice.
But if that exact same bit flip happens in a memory server managing aircraft telemetry or like an automated stock trading system,
the consequences are catastrophic. Airplanes could route incorrectly, millions of dollars could be lost instantly.
so how do they stop it?
Well, that is why enterprise systems never use standard consumer RAM. They utilize specialized modules, starting with parity memory.
Parity memory.
Yes. Parity introduces an automated mathematical check directly into the physical hardware. Normally, data is stored in bytes, right? And 1 byte is 8 bits.
Wow.
Parity memory adds a 9th physical bit to every single byte just to perform a calculation.
Okay, let's walk through the math from the source notes on this because it is brilliant. We are using what they call even parity.
We have even parity.
The rule is that the total sum of all the ones in that 9-bit package must constantly remain an even number.
Exactly. So let's say our initial 8-bit byte of data is 1 and another 0, 100, and a 111.
Okay, so we count the ones. There are 6 ones in that byte.
Right, and 6 is already an even number. Therefore, the memory controller automatically assigns that 9th parity bit a value of 0.
Because the total sum remains 6. It stays even.
Perfect.
But what if the byte was almost empty? Like the example, 000000000.
In that case, there's only one 1. 1 is an odd number. To satisfy the rule, the controller assigns the parity bit a value of 1.
So now you have 2 ones.
Exactly. The total sum is even again. When the CPU comes back a millisecond later to retrieve that data, it recalculates the parity.
And if a cosmic ray flipped a bit, and that total is suddenly an odd number.
The hardware instantly knows the data is corrupted.
That is so clever. But standard parity memory only detects the error, right? It throws up a red flag, halts the system to protect the corrupted data from spreading, and usually forces a hard crash or a blue screen.
Which is an important failsafe. But if we connect this to the bigger picture, a halted system is essentially useless in modern infrastructure.
Yeah, I imagine Amazon wouldn't be too happy if their servers crash every 5 minutes.
Exactly. If a global cloud provider's servers halted every single time a bit flipped, the internet, as we know it, would cease to function. This mandates the use of ECC memory error correction code.
Now, in the past, I've heard ECC described simply as a sprinkler system that puts out the fire, whereas parity is just the fire alarm.
That's a fair analogy.
But I want to push past the metaphor here. How does the hardware physically know which bit flipped out of the billions moving every second so it can actually correct it on the fly?
It moves beyond a simple ninth bit and utilizes complex algorithms. Most commonly, they use Hamming codes.
Hamming
Yeah.
codes.
Instead of just adding one parity bit to an 8-bit byte, ECC memory takes our full 64-bit chunk of data and adds 8 additional bits, making a 72-bit block.
Okay, so a bigger block.
But it doesn't just do one giant parity calculation. It performs overlapping parity checks.
Overlapping. So different parity bits are monitoring different intersecting groups of the actual data.
Yes. Imagine a complex grid. Parity bit A monitors bits 1 through 30. Parity bit B monitors bits 15 through 45. Parity bit C monitors bits 30 through 60.
Oh, it's like a Sudoku puzzle.
Yes.
If one single number is wrong in a Sudoku grid, the intersecting rows and columns immediately conflict.
That is a perfect analogy. If a single data bit flips, it won't just trigger one parity error, it will trigger a highly specific combination of parity errors across those overlapping groups.
Wow.
The memory controller looks at that unique combination of failed checks, and the mathematical intersection points to the exact specific coordinate of the corrupted bit.
Because bits can only be a 1 or a 0.
Exactly. If the controller knows exactly which bit is wrong, it simply reverses it. The error is detected, mathematically isolated, and corrected in real time without the processor ever even knowing it happened.
That is genuinely mind-blowing.
It's incredible engineering.
We have physical modules communicating 64 bits at a time, synchronized perfectly to a clock, pushing data on both the rise and fall of the signal, and mathematically solving microscopic Sudoku puzzles millions of times a second to prevent crashes.
Yep, all happening invisibly.
And yet, despite all of that brilliant engineering, the computer still faces a massive physical bottleneck.
Well, yeah, because the processor is still too fast. We mentioned earlier that a modern DDR5 module might boast 5,600 megatransfers per second. But modern multi-core CPUs can process information so relentlessly that they will literally consume all of that data and then sit totally idle, just waiting for the memory pathway to deliver more. You hit a physical throughput wall.
So here's where it gets really interesting, especially for you listening, because solving this bottleneck completely changes how you should be buying and upgrading your devices.
It really does.
If that single physical pathway between the memory and the CPU is completely maxed out, how do we get more data across the motherboard?
You utilize multi-channel memory architecture. Dual channel, triple channel, or even quad channel.
Okay, what does that mean practically?
Instead of the memory controller communicating with a single stick of RAM over one crowded pathway, it opens independent, parallel pathways to multiple memory sticks simultaneously.
Wait, okay, if opening a second lane is so much better, why do manufacturers sell single 32 gigabyte sticks at all? Like, if I'm building a PC today and I want 32 gigs of RAM, is there a downside to taking up 2 slots with 2 16 gigabyte sticks instead of just buying the one massive stick?
The only potential downside is future upgradability.
What do you mean?
Well, if your motherboard only has 2 memory slots total and you fill both of them with 16 gigabyte sticks, you have 0 open slots left.
Oh, right.
If you decide you need 64 gigabytes next year, you literally have to remove and discard those 2 sticks to make room. A single 32 gigabyte stick leaves a slot open for the future.
I see. But what about for immediate everyday performance?
Oh, for immediate performance, 2 16 gigabyte sticks are vastly superior to one 32 gigabyte stick.
Really? Vastly?
Yes. If you force 32 gigabytes of data through a single channel, it's like cramming all of rush hour traffic into one single highway lane. The cars might be fast, but the road is physically choked.
Everyone is just bumper to bumper.
Right. Dual channel architecture opens a second lane. The CPU can pull data from both sticks at the exact same time, effectively doubling your total peak throughput and drastically cutting down on that idle processor time.
And the hardware actually guides us on how to configure this properly, right? Like if you look closely at a desktop motherboard, the memory slots aren't usually just a uniform block of black plastic. They are visibly color-coded.
Yes. Often slots 1 and 3 will be black, while slots 2 and 4 will be red or gray or something.
And that's not just for aesthetics.
No, this is to visually map out the memory channels for you. If you have 2 matching memory sticks, you don't just shove them into the first 2 slots you see.
Right, you match the colors to activate the dual channel highway. So both sticks in the black slots or both sticks in the red.
Exactly. And those modules really need to be identical to work properly.
Like exactly identical.
Ideally, yes. They should be the exact same capacity, the exact same speed, and preferably the exact same brand and model.
What happens if they aren't?
If you mix and match a high-speed module with a lower-speed module, the motherboard's memory controller is forced to downclock both of them to match the slowest stick in the system just to maintain stability.
Oh, so you're actually punishing your fast memory if you pair it with a cheap stick.
Exactly. You drag everything down to the lowest common denominator.
So what does this all mean? We started by looking at the physical DIMM workspace, understanding why dual inline contacts and multi-rank layouts allow tiny laptop SO-DIMMs to basically punch at desktop weights.
Right.
We decoded the double beat rhythm of DDR memory and the math behind those confusing PC module bandwidth ratings. Multiply by 8, remember that.
Very important.
We explored the overlapping Sudoku logic of ECC memory correcting cosmic ray bit flips in real time, and we cracked the code on utilizing dual-channel lanes to stop your processor from sitting idle.
And by understanding these underlying mechanisms, you transition from just relying on marketing hype to becoming a deeply informed consumer and practitioner.
You actually know what you're buying.
Exactly. When you look at system specifications now, DDR5 5600 isn't just jargon. You understand the throughput it provides, to watch for CAS latency, and you know exactly why you must demand a dual-channel configuration to prevent your system from choking on its own data.
It is genuinely incredible how much complex physics and math is occurring on a tiny piece of green fiberglass.
It is. And this raises an important question, actually. Something the entire computing industry is currently colliding with. The source notes highlight that engineers are rapidly approaching the physical limits of what is possible over these standard copper traces.
Because there's only so much voltage you can push, right?
Yeah.
And only so many megatransfers you can execute before the electrical signals physically bleed into each other and corrupt the data.
Exactly. We are literally reaching the atomic limits of copper and silicon pathways.
Wow.
So if we literally cannot push electrical signals across a motherboard any faster than we are right now, and we eventually max out all of our quad-channel physical lanes, what comes next?
What do you mean?
To keep computing speeds doubling like we expect them to, what radical, entirely new physical architecture will we have to invent?
Oh, man. Are we looking at, like, optical memory, using photons instead of electrons?
Maybe. Or quantum states. We have essentially perfected the electrical workspace, but the physics dictate we may soon have to invent an entirely new realm to work in.
That is a staggering reality to leave off on.
Yep.
We have pushed the literal bounds of physics to make our machines instant, and yet we are already looking for the next dimension of speed. Thank you for joining us today on this exploration into the microscopic heartbeat of your systems. Keep looking closely at the technology around you, keep questioning the specs, and we will catch you on the next deep dives.